Okay. Okay. Sorry for that. Okay, yes, please, you can start. Thank you very much, Anirban.
Okay, thank you. Thanks for inviting me to this IEEE EDS chapter. And thanks everybody who joined this call. And as I'm understanding, it will be recorded. So people who couldn't make this session will be able to also see the recording. Okay, so today's topic that I want to give a talk on is RF technologies for next generation of wireless connectivity. So as the name suggests, there are two things that's coming to picture, right? One is wireless connectivity, one is RF technologies. So if you are connected with either of them, I think this will be an interesting talk from you. And since it's a 1 hour talk and I want to have it more interactive, so I basically have a very overview level of presentation. I won't go to the deep dive nitty-gritty details of each technologies, but if anybody is interested, you are more than welcome to contact me and we can have some conversation on the deep dive. With that, let me start. The outline of my talk would be, so I'll first start with some overview where I will talk about what the journey to the next generation wireless connectivity means. And then I will go to describing some of the key driving factors for RF technologies to address the next generation of wireless connectivity. Next, I will talk about the RF technologies for FR1. So just for people who are not familiar, so 3GPP has different naming convention for different frequency band. So up to 7 gigahertz is FR1. FR2 is 24 to 52 gigahertz today. And FR3, again, it's still under discussion, which people consider as part of 6G, but this will be between 7 to 24 somewhere, and we'll talk about that. I will also talk about SATCOM because it's also important because some of the technologies also can be applied there, and it's also a connectivity. And also I'll talk about sub-terahertz for future. So this will be the crux of the presentation, and then I will summary. So please feel free to stop me anytime you have a question. And of course, I can take questions at the end as well. So let's start with the journey to the next generation of wireless connectivity.
Sorry.
Sorry, yes. So it's not possible to see your next slide, Anirban. So there is some...
Oh, you are not seeing the next slide?
Yeah, we just see the first one, yeah.
Oh, I see the next slide. Is it because of internet being slow or?
No, it's not in presentation mode, it seems.
Yes,
maybe you guys can see
stop
that
sharing.
or not?
Yes.
No, I can't hear you. Can you guys see the next slide or not?
No.
Looks like you're sharing not correct screen. You're sharing not presentation.
Okay. Let me stop sharing. Okay, let me see. Okay, I'm going there. Can you guys see my screen?
Yeah. Okay.
So you guys saw it before, the outline that I just talked about?
Okay, thank you.
Okay, so let me, without wasting time, let me go to the topic. Sorry about the confusion. So you guys are with me, right? You are still in the outline slide. Are you seeing that outline slide?
Okay, thank you. That's fine. Yeah.
Okay, good. Go ahead. So let me start with an overview of the next generation of wireless connectivity. So what's driving the next generation of wireless connectivity, right? So one of the things that's driving is applications, right? Of course, applications has a lot of things. The user experience matters, and it matters that how much battery you are making use of, how fast you are, all kinds of things are there. But before that, let's go at the very high level, the applications part of it. Today, as you know, smartphone is ubiquitous. Everybody uses smartphone. That's not a new thing. Fixed wireless access is another one, getting kind of a traction now. because people working from home, for example, and who don't have fiber, that's an alternate way of giving connectivity for Wi-Fi. And non-terrestrial connectivity is also getting importance because some part of the world is still not connected with fast internet. So for those people, non-terrestrial connectivity is also important. So this is today. Going forward, and some of the things already started, we go to some of the XR application or immersive applications, right? There are some XR headsets already out, but it's not that popular yet. But we believe that in future, this will be one of the key applications that will drive the next generation of wireless connectivity. And I will talk about that more. Surgery, right? Remote surgery is also something being talked about from 5G days. Yes, there is some demonstration proof of concept here and there, but I think it will take more steam going forward. And last but not the least, humanoid, right? A lot of people think that the machine vision, basically the robotics in the industrial sector or even consumer and medical sectors as well, that will be one of the key applications that needs low latency, high data rate, and high reliability communication, right? So basically what I'm trying to say is, as we go forward for the next generation of wireless connectivity, the XR or machine-centric devices with AI or artificial intelligence will ultimately drive the future data traffic. And wireless connectivity has to address that, right? So that is the big picture things. I'm not giving all the applications here, but I think you get the point. So what kind of data traffic we are talking about? Even before going to 6G, as you know, 6G will be launched by the end of this decade, which is 2030. Even before doing that, you can see that from the left-hand side, the data traffic today, even before going to 6G, will be almost like 3.5x. And majority of it will be driven by mobile traffic, right? Like 5G. Yes, 2G, 3G, 4G actually is going down, slumping down, but then fixed wireless access is also there to complement it. We believe that after 6G, with the explosion of AI, XR applications, it will go 10x in the next decade. So there is a paramount need of addressing this data traffic. And that's where wireless connectivity next generation comes into picture. Now, what kind of wireless connectivity we are talking about? So we talk about different kind of wireless connectivity, right? Cellular communication, we are all familiar today. 5G, most of us use it today. Sub 6 gigahertz and also millimeter wave, right? And as I said, FWA, the fixed wireless access, is also getting steam. Wi-Fi. How can we live without Wi-Fi, right? At our home and office and all this thing, Wi-Fi is the mainstay. Today it is Wi-Fi 6, 6E. In future, it will go to Wi-Fi 7, 8. 7 is already there, but it will be kind of taking some ramp. 7, 8, and people are talking about future Wi-Fi with millimeter wave as well, right? From cellular communication point of view, the 6G will drive a lot of new frequencies, and I will talk about at length. One is centimeter band, right? And also it will probably go to more than 100 gigahertz. From the satellite communication perspective, as I said, this is an alternate way of giving connectivity to a broad section of population in the world. Today, it was migrating from GEO to LEO. GEO, basically geosynchronous satellite. LEO is the low Earth orbit satellite. And in fact, you guys probably are aware, there are direct satellite to phone communication also started. Because people go to hiking and other places, they don't have connectivity. If there is an emergency happens, this is the way to communicate. In future, we believe that this will go to higher frequency band. 6G will also have a coexistence with non-terrestrial. The other applications that you guys know, the ultra wideband connectivity, Bluetooth, NFC has been around. And I also include sensing here, because more and more 3GPP is talking about joint communication and sensing. They believe that lot of data that we sense, whether it's audio sensing, video sensing, it can be touch sensing, it can be any kind of sensing, but we have to communicate. How we can marry these two together. And that is one of the things that wireless connectivity for the next years has to also address that, right? Is important. Today we have radar-based sensing. As you know, that ADAS, the automated driving or even self-driving needs some kind of auto radar. But we are thinking about going to even higher frequency for high resolution sensing, including gesture sensing, auto radar, of course, and joint communication sensing. The question is, and which is the crux of this presentation, what RF technology innovations are needed to address this future wireless? Of course, I cannot address everything in a 1-hour lecture with question answers. I'll probably zoom into mostly cellular communication, and I'll talk partly about satellite communication as well. But I'm a kind of, you are more than welcome to talk to me about other wireless connectivity as well. Now let's start with cellular connectivity. As you know, every turn of a decade, there is a one generation of cellular standard evolved and deployed, right? It starts from 1980s, and currently we are in 5G. And we believe that at some point, we will go to 6G, which is the kind of turn of this decade, right? Now, what these generations do, there are lots of different figure of merits, but it's all driven by user experience, right? Because ultimately you have to make sure the user is happy with the connectivity they are getting for the applications they are driving. Now, I'm not going through all the figure of merits, but some of them I'll basically talk about today in terms of RF technologies. Peak data rate, extremely important, right? Carrier frequency, and I'll talk about why people need to go to higher carrier frequency as it's shown here. I'll also talk about energy efficiency. Now, I can talk about a lot of other things like spectral efficiency, data traffic density, and also some of the latency part, but that's a different kind of discussion, right? That goes to the other part of technologies and sometimes it's the firmware software as well. So I'm not going to address that. I'll definitely talk about peak data rate, carrier frequency, and of course, energy efficiency as well. So let's talk about why we have to go to higher carrier frequencies, right? Now, this chart shows today we mostly live in 0 to 7 gigahertz. 0 meaning 450 megahertz to 7 gigahertz, right? 7.125 gigahertz to be precise. But it's highly congested, as you can see, right? Different carriers in the different localities, they get jostle with each other, and it's a very fragmented, right? You don't get too much contiguous bandwidth. And what suffers is basically the high data rate. In order to give you a high data rate, you need a aggregated bandwidth which is as high as possible. Yes, we do carrier aggregation. Basically, the carriers who have, let's say, 2.5 gigahertz and also they have 3.3 gigahertz, they can do carrier aggregation to give you more aggregated bandwidth. But that is costly, and at the same time, it doesn't work everywhere, right? So what we are trying to do, we already opened in different parts of the world millimeter wave band. We call it FR2. And some people even trying to go to FR2 plus, but to FR2 is 24 to 52 gigahertz. But as you all know that it didn't have momentum, right? Because of lots of reasons. Now, for mobility to have a millimeter wave connections, you have to satisfy a lot of things, right? And I'm not going to the details here because of the shortage of time, but you know, the main problem is you need huge densification because of the coverage issue. Indoor to outdoor doesn't work. Even indoor, there is a problem with the attenuation of the walls and glasses and all those things. But millimeter wave is still very relevant because of the fixed wireless access, the last miles, right? Because if there is any alternative to a fast fiber-based bandwidth, it is millimeter wave. So fixed wireless access, millimeter wave is alive and it's getting traction in different parts of the world. And I know, for example, India, for example, they recently did some auction last year and they're deploying FWA, right? It's happening. But mobility didn't get much traction, even though Apple has millimeter wave in some of the US models. What we are trying to do is, there are two things in 6G, right? One is, there is a intermediate frequency spectra between 7 to 24, or people call it 8 to 24. We call it FR3, and I'll talk about that. That is one of the places we want to see whether you can get some of this spectrum, not all, because it's all used for different applications for communication purpose. And the other one is going to even higher frequencies. So FR2 plus or FR2-2 talks about beyond 52 gigahertz. So maybe around 57 to 71 gigahertz, unlicensed band, but people are trying to use those as much as possible. The other one is D band, which is basically 116 gigahertz to 160 gigahertz, in that kind of range. It can be multiple applications, huge bandwidth available, and that's one of the ways to go to higher frequency to give you higher data rate. Now, why we are spending so much time on this? The reason I'm doing it, if you look into every frequency band, it has a pros and cons. So when you go to lower frequency band, yes, it cannot give you the data throughput you need for a highly data congested area like a stadium, like a mall, in the big cities. Yes, you cannot just survive with less than 1 gigahertz. But in a rural broadband where you have to go miles after miles with one tower, this is the only way. So the coverage comes from low frequency. And the same journey continues, right? Mid-band, slightly more data throughput, lesser coverage. When you go to mid-band, in US, we mostly call it a C-band, but it's kind of less and more, 2.5 to 7 gigahertz. Again, much more data throughput, much more helping the mid-band for the data throughput perspective, but lesser band, right? Now you go to millimeter wave, that's already approved and it's already deployed. It gives you tremendous benefit of data throughput, no question about it, but the coverage is limited, right? That's a big problem of millimeter wave. How to address the gap? And that's where the centimeter wave is coming into picture. We call it FR3. Now, as you know, WRC 2023 in Dubai, they actually put some candidate frequencies for FR3. It's not the entire 7 to 24 gigahertz band. It is 7 to 8 gigahertz. And I think it is 13 to 15 or 14.75 gigahertz band. US FCC actually also wanted to open 12 to 13 gigahertz. So basically, these are the kind of bands being considered for centimeter wave. Why centimeter wave? It's a stopgap between millimeter wave and midband, right? And it's also economically viable. It doesn't need that much densification like millimeter wave. But at the same time, it gives you much better capacity than midband and coverage. Just to get this thing more across you, this is a chart I got from my friend Joe Madden, who is from Mobile Experts. He did this very nice presentation in one of our GlobalFoundries forum. His point is, if you look into the LTE or 4G, the cost per kilometer square is very low. Why? Because you don't need too much densification, right? The macro towers is more than good enough. So the cost per kilometer square is very good. But the cost per gigabit is very high. Why? Because they cannot give too much bandwidth to each subscriber. So in order to do that, they basically have to spend more time or money. Now coming to mid-band C-band frequency, which is 3.3 to let's say 4.9 gigahertz. Yes, the cost per GB reduces because you can give more data throughput in a particular kilometer square. And cost is kind of okay. So C-band is a success, I will say. Go to millimeter wave, the cost go over the roof because of densification, right? You have to do huge deployment, NRE cost, CapEx, all kinds of things, right? Of course, it addresses your cost per gigabit because you get huge bandwidth, cost per gigabit goes down. Now the green circle here where I talk about is the gap. So centimeter wave is going to address that, right? It will provide you a very good cost per gigabit. At the same time, it not prohibitively costly like millimeter wave. And that's where centimeter wave is coming. Now let's go to the next topic of my outline, which is key driving factors for RF technologies. So far I talked about the wireless connectivity, applications, frequency spectrum. But in order to achieve that, you need some hardware technologies. And I will talk about RF technologies today. So let's start with the basic radio architecture. For FR1 radio, as you know, it is MIMO based, right? Whether it's a handset or even base station. Base station has a higher order MIMOs, but it's a MIMO based, right? So there, the whole configuration is you basically start with the antenna tuner, antenna switch, diplexers, then there is a transmission switch, receiver switch, LNA, PA, and it goes to the transceiver, right? And ultimately go to the baseband. And this is more or less true for any other wireless application, including Wi-Fi as well. If you go to FR2 millimeter wave or higher frequency, as you know, it's the phased array based, right? It's not MIMO based, it's a phased array based. Yeah. The reason for that is millimeter wave coverage is low, atmospheric attenuation, lot of absorption and others. So they want to make sure they zoom the beam to a subscriber without wasting the energy. Any question? Question? Hello.
So we have some noise online. Be careful with your microphone, please.
Oh, okay. So this is a crosstalk. Okay, that's fine. Let me continue. So millimeter wave is phased array based because they wanted to make sure they conserve the energy and basically give a kind of a zoom beam to the destination, right? Whether it's a receiver, whether it's a machine, or whoever it is on the other end, right? And same thing from the receiver to the transmission side. Now, when you go to the phased array based approach, there are a lot of advantages and disadvantages, right? So advantages is now the transmitted power per PA or the per RF path goes down tremendously. And we'll talk about that just after this. As you increase the number of phased array elements, the power output requirement of the power amplifier reduces. And that is good because it's very difficult to generate a high power with a higher efficiency for any semiconductor, right? Particularly for silicon. So that's one thing. The second thing is, just because the power level is low, you can use silicon, and that means you can do integration. So instead of doing a thousands of component disaggregated, you can do an integrated component here. And I will talk about that. The question is, for FR3, which is centimeter band, which architecture it will adopt? Will it adopt FR1 MIMO-like architecture or FR2 phased array-like architecture? I think this question is still open. People are still kind of studying right now. And again, we'll probably know in the 3 to 4 years' time which direction it can go, right? It can go both ways. Probably it can go one of these ways. And the technology will be different based on that. And the specs will be different too. Now, this is where I was talking about the phased array, right? So phased array tremendously help in a cost-effective millimeter wave radio. Why? Because I know when I used to give a lecture, even probably 5-6 years back at the onset of 5G, they would tell me, you are coming from a silicon foundry, how you can do millimeter wave? It's all 3.5, right? Gas, indium phosphide, on those things. They are correct. That's the way it was before. But thanks to this phased array for commercial communication, we can do a silicon-based phased array. Why we can do that? Because phased array increase the link budget by 30 log n. N is the number of phased array elements. 20 log n on the transmission side, 10 log n on the reception side. How it improves? So for example, if you have 64 PA versus 128 PA, you get an advantage of 4 times the transmitted power and link budget. And the reason you do that is that your PA output, per PA output goes down. And that's where silicon comes into picture. On the receiver side, again, the same thing. The signal to noise ratio increases by 10 log n. And that's the reason that you have to make sure that if you don't have a very good signal to noise ratio, which is very important for a satellite communication, I'll talk about it, you have to make sure you increase the number of phased array. So that is basically the flexibility that phased array brings in. Now, before I go to the RF technology in the next section, let me talk about the key factors that each RF technology adoption needs to drive. Now, there are so many RF technologies on offer, right? Which is good for which application? These things are common for communication. It has to maintain the good coverage, right? Even for Wi-Fi, which is mostly indoor, but still, you have to make sure coverage from one end of your house or office to the other, right? The coverage is important. Energy efficiency. Energy efficiency is important because at the end of the day, a lot of devices are battery operated. But even if it is not battery operated, energy efficiency for the whole globe is very, very important for us, right? So we have to make sure that that is also addressed. Form factor. Now, more content is coming, right? Of course, you guys know about handset. The number of bands offered by a premium smartphone, probably between 40 to 45 bands. It was probably 10 bands, even probably 7 to 8 years before. So more content is coming from the connectivity side. And also there is more cameras, bigger displays, more power management, everything, right? So the form is an issue. Now, it is true for even routers and radio units in base station as well, because more component you have a bigger space. More MIMO you have, more antennas, bigger space. So I think form factor is very important from point of view. And I also put in the parenthesis some of the key stakes here, right? Energy efficiency is mainly driven by power amplifier. Form factor mainly driven by hardware integration. Nothing to do with software, right? Reliability is important. I don't have to spend too much time on it because it's true for any product, particularly for infrastructure. And last but not the least, cost. So the reason millimeter wave didn't adopt 3.5 compound semiconductor because of the cost. Because today millimeter wave is not ubiquitous. Part of the reason is cost, but it would have been even worse if it started with 3.5, right? So that's the reason cost is also important. So with these few things in mind, let's go to a kind of a spectrum of current and future RF technologies. Now, this is, of course, a very global foundry centric presentation. So that's the reason I'm talking about this, because I'm not supposed to talk about any other foundries. What I'm talking about is, for each technology, there is a kind of a targeted application, which it can be used, and some places it is the best for. Starting with bulk CMOS, both 20 nanometer bulk and 12 nanometer FinFET. It is used in, for example, this millimeter wave was first used using 20 nanometer bulk. The wireless SoC like Wi-Fi, cellular transceiver, today it is done on 28 and 12 nanometer bulk, right? Some of the satellite communication, DFE, the digital front end, is also on that. So that has its own place. FinFET, for example, like 12 nanometer FinFET, LDMOS, PA, and with some RF features. It can be used for Wi-Fi SoC, SATCOM, and some transceiver as well, as I said. FDX, which is FDSOI technology. This is basically one of the key technology where GlobalFoundries differentiate. It's a fully depleted SOI technology. What it offers is, it offers you all the advantages of SOI, which is basically device level isolation, less parasitics, going to higher frequencies, but at the same time integration. And this integration is offered at a low power. That's the reason a lot of people use it for wireless SoC, SATCOM, auto radar, even some of the millimeter wave infra application as well. Going to RFSOI, RFSOI is partially depleted SOI. It's also an SOI, but not FDSOI. It's a thicker kind of a box and thicker kind of channel. So it's a partially depleted. Now, this is also very successful in sub 6 gigahertz or sub 8 gigahertz RF front end. For example, the phone that you are holding, I can bet that you are using some of the PDSOI technologies and the parts there, but mainly for the RF front end switches and LNS, right? But it can be used for different other applications like SATCOM and infrastructure as well, and it is being used. Silicon germanium, I will talk about it today about that as well. This is a technology, this is not scaled by like CMOS, right? It's not a lateral scaling, it's a vertical scaling. As a result, silicon germanium technology is a long-standing technology on a particular node. It can be integrated with CMOS like a BiCMOS, but it definitely offers higher frequencies from FTF max perspective. So for some of the front auto radar, some of the Wi-Fi PA, some of the millimeter wave applications, people use silicon germanium. Last but not the least, GaN on silicon. Now you can ask the question, you are coming from a silicon foundry, why you are talking about GaN? We realized for some of the application, particularly centimeter wave FR3, GaN probably one of the most suitable technologies. The reason being, GaN is a wideband semiconductor. It can withstand more voltages. As you know, as you increase the VDD or the drain voltage, you can have more efficiency. So that's the plus. The second thing is the mobility, right? The channel mobility of the GaN is extremely good. You can use it for your higher gain, right? And at the same time, GaN also offers you more bandwidth. So efficiency, higher power output, and bandwidth. What else you need? Only thing you have to make sure, can you do in a cost-effective way? And that's where GaN on silicon come into picture. I'm sure most of you are kind of familiar with GaN on silicon carbide, and that is the technology being used today in infrastructure, right, in the power amplifier. We are talking about a solution which is more cost-effective, and it can be used in handset as well. And I will talk about that. We are also talking about how to integrate all these technologies, not all technologies, but some of them, with each other. It can be a monolithic integration, it can be a heterogeneous integration, and I will also talk about that. So with this brief introduction and the key driving factors, let me go to the next topic, which is the crux of the presentation today, the RF technologies for different frequency band and application. Please stop me if you have any question. So let's start with FR1. So this is a chart we have been showing over time. As I said, I came from IBM. When IBM got absorbed into GlobalFoundries, the same technology roadmap continued, right? So from 2008 onward, and my team is one of the first team in IBM who did the enablement for 7RF SOI. So with that journey, we only went forward, never looked back. The reason being, at that point, gallium arsenide was the only technology for switches and definitely for LNA as well. So we found out RF SOI is not only cost effective, it can match the performance, and at the same time, it can provide you integration, which at that point was not a big thing. But today, with the BOM that you have in a smartphone, it's an absolute necessity. If you look into the board of any smartphone, whether it's the RF board or the main board, you'll see there are so many components there. People want to integrate to get more space for more components. It wouldn't have been possible, at least from the connectivity perspective, without this RF-SOI technology. As I said, RF-SOI is a partially depleted SOI. It has a slightly thicker box or the oxide, and also slightly thicker channel than FD-SOI or fully depleted. What it offers is, it offers higher voltages, higher isolation, and better parasitics, and also it provides lesser insertion loss. It's extremely important. Remember, I talk about the higher coverage and power efficiency. If your switch losses are more, whatever you emit from your power amplifier or whatever you are receiving from your LNA gets much more difficult. So that's where this RF-SOI switches come into picture. I'm not going to the every phase of this journey, but all I can tell you, currently we are on 8SW. It's a 130 nanometer SOI technology with a front end which have like a 65 nanometer kind of thing, which is for LNA. It provides probably the best LNA on offer for sub 8 gigahertz for any technology, right? Of course, switch is also the best. The factor that we use for switch is R-on, C-off, the product of R-on and C-off. One is insertion loss, one is isolation. The lower the number is, the better. Today, we have achieved less than 100 femtosecond. Our goal for 9SW, which is already publicly announced, it will be introduced sometime later this year in a product, or probably later next year. We are going even further, less than 80 femtosecond. And we are also shrinking by more digital density. And that's the reason we are going to 90 nanometer kind of a digital technology for this. So this is the journey we took for switch and LNA for FR1. Where we will go next? Now, we finding it out is extremely difficult to continue this exponential growth, because we have made so much big stride. At some point, it's going to saturate, and that's going to happen. So what is after 9SW? So of course, we can go at least one more generations, but we have to also think where the diminishing return coming from. One of the way to look at it is, can you do much more shrinking by footprint reduction? There are different thoughts here. I'm not going to the detail, it's a busy chart. I'm just showing some of the thoughts with our collaborators, IMEC. They believe there's a vertical stacking is one way. It's like this, right? When you go to a big city, you see high-rise building. Because the footprint of the total area is less, demand is more. So you cannot have acres of land and kind of a ranch style home, right? So the same idea here. When there is a form factor issue, you stack. Maybe you stack RF with power. Maybe you stack one RF with another. And it can be wafer to wafer stacking, die to wafer stacking, or die to die stacking. Depends on what is convenient or what is feasible. So that's, in my mind, the future wireless probably will intercept this kind of integration going forward for RF-SOI. Okay, and I can take questions more than I'm more than happy to do that at the end if you want. Let's talk about different other frequencies. As I said, the power amplifier is a key for driving efficiency, and of course for coverage as well, because it's the main ingredient for transmitter. This chart is shown by IMEC. But the actually underlying chart is done by Professor Hua Wang. I know some of you probably know. He is now in ETH, Switzerland. He was in Georgia Tech. He is our long-term collaborator. And his students publish these charts almost periodic basis. What this chart says on the lower left-hand side is frequency versus PSAT. PSAT is the maximum power output the power amplifier can give. As you go to higher frequency, the power output drops. And there is something called Johnson limit, right? It's basically there is a product. So your gain bandwidth product or the power bandwidth product reduces. But the color here it shows that if you have to go to higher power, you have to go from CMOS to SOI to SiGe and then 3.5. If you have to go to higher frequency, you have to start from silicon CMOS to SiGe to 3.5 materials. Now you can see the over preponderance of red here, which is GaN. And that's one of the topic I want to mention it here. This inset, which is called FR3, basically between 7 to 24 gigahertz, it's shown here. And basically, I showed in a zoomed way what the colors mean here. You can see that to get to higher power of PSAT for this frequency range, GaN is a very good alternative. I'm not saying GaN is the only alternative here from the power amplifier perspective, that this is a good option. So that's the reason GlobalFoundries decided to basically not just being only silicon foundry, start looking into GaN. We are developing GaN on silicon technology for both infrastructure, FR1 and FR3, and also for handset, particularly for FR3 as well. We can use it for other purposes as well, and even higher frequencies. The point that I'm trying to make here is, as I said, what are the key driving factors for adoption of technology? You can see it here. The power output, efficiency, integration, and cost plays a big role. It is not evident from this chart because efficiency is not here, integration is not here, but these are also very important to consider, and cost. And that's the reason we believe GaN on silicon can probably replace GaN on silicon carbide if the performance is good. Okay, we can take questions on that as well. Before going to millimeter wave FR2, I start with this chart because that really shows where technology differentiation comes from. This is a chart. Basically, I collected from different sources. If you go to a Verizon tower or access point, you can see there is a kind of a big boxes or cylinder, and there is a small one. The big boxes use for millimeter wave phased array 20 nanometer bulk technology. On the right hand side, some carriers use vendors who use silicon germanium. When you use silicon germanium, it's not only more efficient PA, it can generate more power. So coverage is better, efficiency is better. So they don't need to have a big box. They can have a much smaller element. So factor of 4, right? And a 28 gigahertz, 1,000 elements become 250 elements. And that's the reason that technology selection is so important. You might argue that SiGe is more costly wafer-wise, but solution-wise, it is not. In fact, it is more cost-effective. If you consider reliability, long-term reliability, it's much more cost-effective. So I start this discussion because that's where the flexibility of phased array comes into picture in millimeter wave. Now, what is the architecture of millimeter wave? Now, I talked about the phased array architecture. I'm going to more details here. There are different options here, both for FR2, 24 to 52, and even going beyond. Like I talked about 57 to 71, FR2-2, and even beyond, right? So the left-hand side is, if you go for higher integration. By higher integration, I mean the radio integration, not the digital part of it. The digital part is the modem part of it. Of course, that is going to the bleeding edge node, right? So 7, 5, 4, 3 nanometer. I'm not talking about that. I'm talking about the purple section on the top next to the antennas. So if you want to do more integration, including up-down converter, you can go to 28 bulk, which is the way it started, and 22 FDX. The advantage of 22 FDX is it's much more power efficient and give you more power output from the PA perspective. If you wanted to get only integrated FEM, not the integrated and up-down converter together, because you think you need to get more power, partially depleted SOI is your answer. We have 45 RF SOI, 45 nanometer PD SOI. We are also developing 45 RFE, which is a kind of a derivative or cost-effective version of it that can address that. Definitely, it is much better compared to bulk. So far, the transmitter output is concerned and efficiency. If you want to go even further, like base stations, for example, you need huge coverage, right? And there you split the front end also into two parts. The best switches and LNAs you can get in RFSOI, 8SW, 9SW I talked about. And that is true even in millimeter wave. We have found that switches are very good. LNAs are also good, but you can use some other LNAs as well. The point is you have to distinguish the PA. Because PA, now you have to use the best technology, either silicon germanium, GaAs, or GaN, right? And now you get the best of the both worlds. Best receiver, best PA transmitter, and now you're not talking about integration, you're talking about the raw performance. So that depends on your application and need, you can adopt any of this architecture. Why it matters? It matters because if you use 22 FDX, as I said, it's more for integration. It can integrate the radio in the sense it can integrate the front end, transceiver, the data converter, and SerDes. All of them can be done in a very power effective way. The reason it can be because it offers higher breakdown voltage. it has more voltage headroom, and that gives him a lot of design flexibility and reliability. Some of the performance in front of you, I am not going to the details line by line here for the sake of time, but you can see that both for a transmission and receive perspective, like noise, NF mean, and also the self gain, it's an excellent technology from integrated platform. I would say this is the best integrated silicon technology available for millimeter wave. Now let's switch gear for satellite communication. I said that I'll spend some time on satellite communication because this is very important and getting more traction. So when you talk about broadband satellite communications, people are very familiar with geosynchronous satellite. This has been around for a long, long time. What we are doing is a low Earth orbit satellite, which is not stationary, which is moving with the Earth, right? So basically you have a constellation and you can at least see one satellite during any time of your day, right? So you need a vast constellation of satellites. So as you know, SpaceX, OneWave are the two key providers right now. Amazon also publicly announced they're also working on it. So a lot of people, the big players are coming into this. But what is the key from our technology point of view for today's discussion? The two things has to happen to make it ubiquitous. One is the cost of the ground terminal and also the data rate you achieve. Now, both are not a kind of a no-brainer. The reason is when you do a phased array-based ground terminal, it's not bulky. It is electronically steerable. There are a lot of advantages of it. But people want to see whether it is good enough to buy it compared to Wi-Fi. That's number one. Where Wi-Fi is not available, there also people have to think about how much they have to spend to get how much bandwidth they're getting, right? So these two are kind of the key figure of merits. Now, how we'll address that? So the second thing we can address that by addressing the carrier to noise ratio. As you know, when the carrier to noise ratio become lower, your data rate suffers. So this equation shows one of the key factors for carrier to noise ratio is G by T, which is the antenna array gain by the antenna temperature. Antenna temperature is the effective temperature that basically get translated, and that determines the noise factor, right? So if you want to have more carrier to noise ratio or more data rate, you have to have more antenna gain. How can you get more antenna gain? From the phased array, more number of elements, right? But the more number of elements means it has to be huge space and your cost goes up. On the other hand, the denominator T has to be low as possible because then the noise figure will be low. For the noise figure to be low, you have to have an LNA with the lowest noise figure possible. If there is any commercial application where you have the maximum sensitivity of receiver, this is the application. So we basically understand that, and I'll show you in the next chart. We develop technologies, we have multiple technologies, by the way, for the as much noise figure improvement as possible. That way, you can reduce the number of arrays and also with the cost. For the payload satellite, I think efficiency of the power amplifier is also very important because with a large array, so many power amplifier dissipating power, the heat is a very important factor for a satellite. So there it's also important. With this few brief background, let me show some results here. I'm not going to disclose the technology here. We have used a lot of technologies here, right? But some of the technology is better for power amplifiers, some of from LNA. We actually kind of landed up with this technology, which is cost-effective specialty technology, which gives very high frequency power amplifier on the left-hand side. You can see the peak PAE is around 50%. And the LNA, it is probably the best LNA noise figure people have achieved so far. And this is even less than it's probably around 0.8 kind of a dB noise figure, right? And descent gain as well without sacrificing anything. The reason I'm showing it here is for the next generation of wireless connectivity for SATCOM, you have to adopt a cost-effective technology with the maximum receiver sensitivity and high efficiency power amplifier for satellite. Let me go a little bit faster. I have 10 more minutes, so I want to open for questions. So last phase is for sub-terahertz. By sub-terahertz, I mean more than 100 gigahertz. Now, I understand that this is not probably going to happen anytime soon, but people have started looking into that. The reason they're looking into that is not only because of the spectral crunch, also because of the fact some of the places that like sensing, high resolution sensing can be only achieved today by infrared or optical. What is the cheaper alternative to that? That's the sub-terahertz is being placed. And same is true for image-based auto radar as well. The challenge here is as you go to higher frequency, the the total form factor of the array reduces. And when you put an RFIC behind it, it has to also scale. How can you scale in RF? It's very, very important. At the same time, when you reduce that size of the RFIC at higher frequency with more inefficient PA, thermal challenges come into picture. So this is a big challenge and it needs to be solved. This is a chart. I don't want to spend too much time, but I want to tell you, yes, I have to admit, if you go by raw performance at sub-terahertz, indium phosphide is the best. As you can see from the outer, gray colored chart, which is indium phosphide. But the performance is not everything, right? I told you the reliability, cost factor, integration, all this thing comes into picture. Now, if you go to the other end from bulk CMOS, yes, it can provide you a lot of integration and cost, but performance is not up to the mark, at least in this frequency range. So what we'll do then? There comes in the PDSOI and FDSOI. They are intermediate. They can provide the integration at a slightly higher cost, but they're also getting very high performance at D band. I don't have the results here, but I can send it to you if you want. 140 gigaband phased array achieved with both 22 FDX and 45 RFSOI. But last but not the least, silicon germanium. Extremely important to understand. Silicon germanium as a technology can provide the best return of your bucks. The reason being, it has highest Fmax. It also has the no need for scaling. The only thing, and it's much cheaper than 3,5 material compounds, right? With GaN and indium phosphide. So then, how I can achieve integration and cost? That's the marriage between CMOS and SiGe. And that's our recommendation at this point. If you want to stay in silicon for sub-terahertz, this is probably the best solution. Now, what is the best solution? You develop a sub-terahertz silicon germanium HBT, right? And people have shown that it can, Fmax can 600 gigahertz. There's a roadmap to cross 700 gigahertz. And you need that kind of Fmax for sub-terahertz. Once you achieve that, how you get the control electronics, logic, and everything together? That's where CMOS comes into picture. Now, there are two ways we can achieve that. We can do a monolithic integration of a bi-CMOS with SOI, having all the advantages of SOI with silicon germanium transmitter, or even LNA as well. Or you can do a heterogeneous integration, where there'll be a die or wafer of SOI, and SiGe will be on top. It can be top or down based on how you want to do power dissipation. I'm not going to those details here. But the point is, we believe this is probably one of the best options for going to higher frequency, where you have to address integration, cost, performance, efficiency, and at the same time, reliability. I don't want to spend too much time on this chart, just to show some of the literature to show what people have achieved in D-band in silicon. Yes, indium phosphide is very good. GaN is also very good for some demonstration has been shown. But silicon is not far behind. And silicon germanium is the best. As I said, we can do some kind of a combination of silicon germanium and CMOS. Same thing for LNA. If you look into the noise figure and gain column, you can see that, of course, indium phosphide is very good. We are not showing GaN here, but SiGe is also very good here compared to any other silicon technologies. With that, I will go to my last landing page. From GlobalFoundries perspective, from silicon technology, we talked about PDSOI, we have talked about FDSOI, and we have generations of that going towards higher efficiency, more digital scaling, and higher frequency. But when you go to even higher frequency, we believe that silicon germanium integration with PD and FDSOI is the way to go. There you get the best return of the bucks for the integrated radio for higher millimeter wave and sub-terahertz. This is my summary. As I said, that next generation of wireless connectivity needs to drive coverage, data rate, but optimum energy efficiency is the key. And there are multiple challenges here from performance efficiency perspective and integration, not to talk about the cost as you go to higher frequency. But as I discussed in a brief manner, there are future technologies with their roadmap, at least from our perspective, where differentiated silicon like RFSOI, FDSOI, SiGe, and some 3.5 material like GaN and maybe indium phosphide at some point can address those things. With that, I'll wrap up here. Thank you. And I'm open for any questions.
Thank you very much for this great presentation about RF technology for future wireless connectivity. covering many different topics. So, do you have any question? Maybe there was a question on the chat.
One person also wants Vladimir.
Oh yeah,
Yeah.
Vladimir. Yeah. Okay.
Yeah, just raise the hand. Can you hear me?
Yeah.
Yes, I can hear you.
Yeah, thank you for the interesting talk. I appreciate it a lot. You mentioned several times silicon carbide on gallium nitride, but it's not on your slides. And in terms of mobility band gap, it's quite close to the gallium nitride. Can you
Yes.
comment on this material?
So absolutely, I think you are on the dot, right? I didn't talk about because GlobalFoundries doesn't offer gallium nitride and silicon carbide yet, so that's the reason I stayed away from that. I could have copied some literature, but I didn't do that. But let me answer your question. Yes, GaN on silicon carbide, as you know, is existing in a product in a base stations. If you go to any base station, particularly with C-band and higher frequencies, the last stage of the transmitter is GaN on silicon carbide. From the mobility perspective, this is definitely good. But the most important thing for silicon carbide is the thermal budget, right? Because the silicon carbide offers that. So with that, a lot of problems and flexibility in the design of the system is solved. So definitely, I will say that this is one of the best technology from that perspective. But as you think about that, with the cost in mind, base station is one thing, right? When you go to UE or user equipment handset, if they want to adopt, it will be a big barrier. So how do you address the barrier? And that's where GaN on silicon comes into picture. So I'm not saying GaN on silicon is any way better than GaN on silicon carbide from the mobility perspective. What I'm saying is, and also thermal perspective, but if the power level is not that high, you can have an arrangement of dissipating that power. And if you have that, GaN on silicon is an alternative. That's all I'm saying.
Okay, but you do not consider silicon carbide itself. You consider only
silicon
stack
carbide. Okay, I got your question. So silicon carbide, we don't consider for RF, we consider for power. Yes, GlobalFoundries also looking into that as well for extremely high power. Silicon carbide is probably one of the best technology. From the RF perspective, I don't consider silicon carbide for many reasons. Mobility, of course, you mentioned that. But the other thing also, think about this way, right? You have to mention at the end of the day, if you want to have a volume production, you have to have a silicon base. And that's the current understanding. In fact, if you talk to a lot of people in IMEC, they're considering how to integrate indium phosphide as silicon for the same reason. So I don't see silicon carbide just as a material will come to RF. But for power, absolutely agree. This is one of the best technologies available.
Thank you.
Okay, thank you for this question. So is there any other question? So there is a question on the chat. I don't know if the colleague is again is online or not, but so I can. So the question is, what is Aaron and VRF max of BS 8SW and 9SW?
Oh, okay. So yes, so that's a good question. So I showed the Aron COP product, right? The reason I do that, and we don't talk about Aron, because you can optimize either reducing Aron at the cost of COP or reducing COP at the cost of Aron. We don't talk about it because if I tell you a number, I can give you a very good number. Doesn't mean anything. The reason is, if I do a good Aron, which is basically by making less number of stacks, the VR suffers. And your question is very valid. So the figure of merit is Aron COP divided by VR max, right? And your question is really good because we have to always talk about how we can optimize Aron COP and at the same time without reducing VR max. So let's talk about that, right? So for a particular switch, for example, like a tuner, you probably see that voltage drive can go to even up to 70 volt. It's a huge kind of a voltage swing, not the DC voltage, right? Now we have to do immense number of stacks. What we do is, with our technology, with 8SW and 9SW, we have to do lesser number of stacks because your VR max is more, right? And again, I am not quoting the number of VR max because again, the Aron CF will come into picture. So we have to always talk about Aron CF and VR max together, not individually. But the point is, you can have a best technology which has the highest VR max and the lowest Aron CF, and the ratio would be also the optimum. So that's what is offered by 9SW. and it is almost like 10% more than 8SW. That much I can tell you. Any other question?
So yes, hello Anirban, Ivan speaking.
Hi,
Could you hear
Ivan.
me?
How are you doing?
Fine. So maybe one question. So you have presented that you are segregating, I think that specifically the wireless technology through different bands, so FR1, FR2, FR3, and possibly sub-terahertz. And you have presented that you have different options, so many silicon technologies, 3.5 material, but that you are looking also the 3D stacking technologies. So we can see through this different approach that there are maybe a choice between monolithic integration, 3D stacking integration, choice of maybe CMOS scaling versus, I think, 3.5 material. So what is your mindset about for this FR3 and possibly terahertz? What could be the best option? So because you have presented many, I think, technologies that could fit, but from your perspective, what could be the best option in terms of technologies?
So for FR3, that's a good question. As you know, the whole world is very focused on FR3 because carriers, particularly all over the world, they're looking for some spectrum. And FR3 might provide that if it is recommended by ITU and allocated by different regulatory bodies of different continents, right? Now, coming to FR3. Again, the jury is still out. It will be an integrated offering of a phased array based. If it is a phased array based, of course, it needs more densification. And at that point, what will happen is 22 FDX like technology will have its say. Because we have proved 22 FDX for millimeter wave. Some of you know that already. If you go to some of the latest product, you can find out to 22 FDX with millimeter wave phased array. So there is no reason it cannot go to lower frequency. So that will be the technology for integration perspective. But if it is FR1 like, it is not integrated, it will be discrete. That's where I think the RF-SOI LNA switch and GaN on silicon PA will be the right combination. Now, when I say GaN on silicon, I am also including GaN on silicon carbide on the base station side because that competition has to be happening. But GaN on silicon is a very good offering at this point in my mind, both for infrastructure and handset for PA, and it can complement or even replace to some extent gallium arsenide PA. But the switch LNA, I still consider it's a RF-SOI technology.
Okay, thank you. Any other question? Maybe not. So it's already 6 p.m. In France. So it is now 9 a.m. in the West Coast. So if there isn't any other question, I would like to thank you again very much for this great talk. So in the framework of IEEE EDS Distinguished Lecture. And as mentioned by Anirban, so if you have any other question, maybe in the future, you can keep in touch with Anirban for the future. So thank you very much again. And hopefully we'll see you in France, Europe, or Grenoble area, maybe in the future. And so thank you. And thank you also for all the participants for this distinguished lecture.
Thank you.
Bye-bye.
Thank you very much. Thank you.
Thank you.